Okay, so hi everybody. Thanks for listening in. In this presentation, I'm going to be talking about the giant planets Jupiter, Saturn, Uranus, and Neptune. Now, we've already talked a little bit about these objects in the context of planets in other solar systems. One of the things I always want to emphasize is these are amongst the most alien environments anywhere in our solar system. Even places as hostile as Venus, we could imagine being on, in the sense of there's a surface with an atmosphere. There's something we can stand on. And maybe the environment's very hostile, but you could imagine some sort of robotic exosuit that might allow you to walk on those places. The thing about these objects is they don't have any surface to speak of. They are entirely atmosphere. And if you go into them, you just get more and more atmosphere, and it gets more and more extreme. So there's no place to stand on the surfaces of these bodies, which is something that we just have trouble grokking. In fact, everything we see about these objects, including these clear features, are, of course, storms and clouds. Those are the things we can see. The most famous of these is, of course, the Great Red Spot on Jupiter. This is a storm that is comparable in size to the Earth that has been around for hundreds of years. And all of this other structure that we see on Jupiter are basically clouds and storms. It's basically all meteorology. Now, and we can see that by the fact that, the shape and sizes of these storms change over time. For example, the Great Red Spot has been getting steadily smaller over the last 20 years. Maybe it'll start to grow again. Maybe it'll actually dissipate in the next decade or two. That's not impossible. We have a combination of features that are long-lived and other features that just last for a short period of time. And this is true of Jupiter, where we have all of these very clear and very prominent storms, but it's also true as Saturn as well. Now, Saturn generally has more muted cloud features, but it does have a few things that are long-lived. Its most famous one is this feature around its North Pole, which looks honestly like a hexagon. This is actually a wave in Saturn's atmosphere. It would be causing something similar to this, some kind of wiggle in the position of one of these basically jet streams. But because it's close to the pole, it actually looks like a hexagon rather than just a six-folded wiggle. This thing has been around for 30 years, and the only reason we don't know it's older than that is we didn't have the technology to see it clearly before that. At the same time, Saturn also shows evidence of short-lived features. Normally, Saturn in visible wavelengths looks fairly bland, but in 2010, there was a sudden appearance of a gigantic storm that appeared and distributed material all the way around the planet. This actually happens roughly once every Saturn orbit period, which is about 30 Earth years. So we see these sorts of combinations, and even in the more distant planets, Uranus and Neptune, we see the same thing. When Voyager flew by Neptune back in 1989, it saw a very large dark storm, which was called the Great Dark Spot. And people thought, oh, that's like Jupiter. There'll be this feature that lasts forever. It disappeared within a decade or two. There are other storms which are happily around, and there are different clouds, et cetera, some bright, some dark. But Neptune is also showing these sorts of variations. And Uranus does as well. But Uranus's clouds are heavily modified by its extreme seasons. Now, remember, seasons happen due to the fact that the spin axis of the planet is tilted relative to its plane of its orbit. Now, it turns out that Saturn and Neptune have tilts like Earth's, and they're actually about the same size. They're between 20 and 30 degrees. Jupiter has a very small tilt, so it does have kind of seasonal changes, but they're fairly subtle. Uranus's tilt is almost 90 degrees to its orbit, which means that it is basically on its side. That means it has very extreme seasons. This is a graphic showing Uranus going around the planet. Here's the North Pole, here's the South Pole. There's actually debate about which one's which, because which one's north and which one's south is kind of an arbitrary choice. But turned out that in 1986, the South Pole was pointed towards the sun. Now, as we approach 2028, the North Pole is starting to point towards the sun. In between, basically its equator pointed towards the sun. This is very extreme seasonal variations, much more extreme than any other of the classical planets. And this has significant implications for the way it looks. For example, when Voyager encountered Uranus in 1986, it was only able to see one hemisphere, and there was basically, the pole was in the middle of this, and if you look at this, there's literally no clouds whatsoever. People inferred that that Uranus in particular, was kind of boring atmospherically. But as time went on and we went closer to when the equator was on it, and thus more like normal planets, storms started to appear, like here and here. So Uranus's cloudiness changes over the course of its seasons. And it's going to be interesting to see what happens as we get back into this configuration. Does that activity stop? Is that repeatable? Or is that just the way Uranus happened to look when the Voyager spacecraft flew by? Now, more fundamentally about this is that these atmospheres are surrounding something, but what we need to realize is we can only sample the very outermost layers of these planets in any meaningful sense. When we look at the atmospheres of these planets, the parts we can see, the parts we can probe, they are all composed primarily of hydrogen and helium. Hydrogen can be detected by spectra. Helium is harder, but there's some hints that it's there. There's also some amount of other molecules, particularly methane and ammonia. The clouds we see on Jupiter and Saturn are primarily made of ammonia. The clouds we see mostly on Uranus and Neptune are made primarily out of methane. Now, the problem is, though, we can only see things down to a fairly shallow depth. Remember, these are, 4 to 10 times the size of Earth. And it's natural to ask, well, what happens as you go further down? And this is something we've explored a bit for Jupiter. It was a probe called the Galileo probe, which actually went into Jupiter. And it partially went in to measure the atmosphere, actually measure the amount of helium with in situ devices, and also to measure winds and other such things. This thing only got down to 24 bars, which is 24 Earth atmospheres. So it didn't even get as deep as what would correspond to the surface of Venus, but it got 150 kilometers down, which is a fair distance. But it's only a small fraction of the size of the planet. This is the only part we've directly sampled. So a natural question is, what's happening further down? What's happening deeper inside these objects? Since we can't sample that directly, we need to use other methods to figure this out. And it's based on things like their density, which we've already talked about a bit. It's also based on measurements of these objects' magnetic and gravitational fields. Now, we've already talked about what the densities tell us. The densities tell us something about their composition because basically there are two forces that determine the size of a gaseous or volatile-rich planet. If you took, say, 300 Earth masses of hydrogen and helium, gravity is going to pull everything towards the center. So it should all collapse. But it doesn't, because basically those molecules are moving around and they just bounce off each other. Those collisions resist that compression. And the final size and effectively shape of the planet is set by a balance between those two forces, gravity pulling in and the collisions amongst the molecules pushing it out. And the exact size depends on the types of molecules you have. Turns out that Jupiter and Saturn are basically the right size and mass and density to be made almost entirely of hydrogen and helium, basically like the sun. Uranus and Neptune, on the other hand, because they are smaller but more dense than Jupiter, that doesn't work. There needs to be other molecules inside Uranus and Neptune, heavier atoms, basically that are easier to compress. So this is why we distinguish Jupiter and Saturn, which are conventionally called gas giants, from Uranus and Neptune. Uranus and Neptune are often called ice giants because one of the primary components of these bodies is probably water, literally H2O. Could also be things like ammonia and methane. These are all materials that are ices if they weren't inside a giant planet. They are almost certainly not in the frozen solid phase inside these bodies. So it's a bit of a misnomer. And we've talked about how these are somehow a transition between gas giants and solid bodies. So there needs to be work on the names, but currently the name for them is ice giants. Now, there is something about this, though, that's worth mentioning. So we have a sense of what their composition is, but there's something unusual about these bodies, in that even though they're made primarily out of hydrogen and helium for the gas giants, and probably have a large fraction of water for the ice giants, all of these bodies are able to generate strong magnetic fields. These are plots of the magnetic fields for all of the giant planets compared to Earth. Each one has a separate scale bar at the bottom, and it's basically how strong the magnetic field is coming through the surface. So on Earth, we have the magnetic field coming out on one side and going in on the other. And it ranges from -80 to +80 microtesla. That's just a unit of magnetic fields. If you look at Saturn, which has a very kind of weirdly symmetric magnetic field, or Uranus and Neptune, which have very blotchy and weird magnetic fields, the ranges are kind of similar. So the magnetic field at the surface of these objects are similar to those of the Earth. But remember, they're bigger than the Earth. So that requires an even stronger source of magnetic field. Jupiter has a magnetic field that is 10 times stronger than any other planet in the solar system. Jupiter's magnetic field is by far the strongest of any object outside the sun. And that's actually a practical problem because magnetic fields affect the motion of charged particles. They affect the motion of currents. That's how dynamos and motors work. What that means is Jupiter's powerful magnetic fields actually trap a lot of fast-moving charged particles that just happen to be around in space. This is actually a practical problem for exploring Jupiter because it means your spacecraft has to fly through fast-moving charged particles, which do things like break computers. So this is a major hazard. And unfortunately, these populations of radiation, it is effectively radiation, is in the same region as some of Jupiter's moons. So this thing is practically a problem. It also leads to pretty things like Jupiter having very powerful and pretty aurora, just like on Earth. Earth's aurora is due to material that is funneled along magnetic field lines into the atmosphere. That happens at Jupiter as well. But it's kind of a double-edged sword. Jupiter has some very interesting phenomena, but it's also very hard to study close up. But more fundamentally, how the heck are the planets even doing this? When we talked about the magnetic field generated by Earth, I said that you need a liquid metal to do this. Liquid metals are needed because you need to set up currents to generate magnetic fields, just like you would in an electromagnet. In principle, you can do that in a solid, but it actually is much easier to have it happen in a liquid. If the liquid starts to flow, it generates a little bit of current, which can generate a magnetic field, and it can create a runaway process where a bit of a magnetic field creates more of a current, which creates more of a magnetic field. Now, you might say, wait, oh, okay, if there's a strong magnetic field, there must be a metallic layer deep in the core, there must be iron somewhere in these bodies. And that's a reasonable thought, that there's some iron-rich metallic material deep inside these objects. The trick is, even if there was, it isn't strong enough to produce the magnetic field we see. We need a much bigger magnet, a much bigger electromagnet. And it turns out that the major components of these objects can produce a magnetic field. Specifically, for the gas giants, hydrogen can produce a magnetic field. Now, hydrogen at conditions like they are here on Earth is a gas. It is not a metal. But on Jupiter and Saturn, we're talking about a lot of hydrogen, and it's getting very heavily compressed as you approach the center. In fact, it gets compressed so much, it's dense, it begins to enter what's called a metallic phase. If you compress hydrogen gas enough, it turns from a gas into a fluid metal. Now, I used to just have to say that, but after 2017, I can actually show you a picture of that. People can do experiments that compress briefly chunks of materials to the conditions you have inside these giant planets. This is a little blob of hydrogen. This is it, and it's at high pressures. It's called 205 gigapascals. It's basically 2 million Earth atmospheres. So this is already highly compressed, and what we're looking at is a light behind it shining through it. So it's a transparent gas, like it is normally. If you bring that up to 4 million Earth atmospheres, it starts becoming opaque. It's now blocking the light coming in from behind. That makes sense. If you compress anything, it'll start becoming more and more opaque just because it becomes more and more packed together. As you approach 5 million Earth atmospheres, then the light from behind is gone. What you can now see is light reflected off it from that's coming from above. This is becoming reflective. Reflective is a property of metal. This is a metallic form of hydrogen. And it has all of the other metallic properties, including conductivity, including the ability to sustain current. So what we think is going on here in these bodies is they're dense enough at their centers for hydrogen, which is their primary constituent, to act like a metal, which would be consistent with their very powerful magnetic fields. Now, for the ice giants, the situation's a little harder. There is evidence that water does something kind of similar. It can behave a little like a metal under certain conditions. Whether that's what's going on or something else is still an open question. But these magnetic fields are telling us that these things have unusual properties at their centers. Now, but at the same time, that means that their magnetic fields alone aren't evidence that there's metal or rock at their very centers. We don't need that to do that. It would be natural to think that there is an object made of rock and metal at their very centers. I mean, if you drop a rock in atmosphere, it will fall towards the center, and rocks have fallen into Jupiter, Saturn, Uranus, and Neptune. They might have even been there from the very start. The easiest way to imagine making planets like this is to say a planet like Earth was forming, a solid planet, and then that planet pulled in hydrogen and helium gas to form this enormous atmosphere that eventually dominated the entire planet. If that's correct, you would expect, okay, there's a planet inside. I'll also say this would make us feel better because it means, okay, I would never survive the fall through Jupiter's atmosphere, but there is a surface down there. It's just really hard to get to. I could stand on the surface of this rock metal core, and I'd be surrounded by metallic hydrogen instead of surrounded by air, but I can imagine that. This is something that people have been very interested, not just for that reason, but also because this is potentially relevant for how these objects came to be in the first place. And so there have been scientific missions which had goals to figure out, is there a solid core inside these bodies? This was one of the things that was done by the Cassini spacecraft, which was a mission to Saturn, and it is one of the prime science drivers of the Juno mission, which is currently in orbit around Jupiter. The way they were trying to study this is by measuring the planet's gravitational field. If there is a dense core, that's an extra gravitational pull that you can notice if you're flying by at very low altitudes. You can notice, oh yeah, there's a really dense thing in the middle. Making that measurement, especially when that object is much less massive than the planet as a whole, is challenging. The Cassini data are, in terms of the gravity field, are still ambiguous on this point. The data for the Juno spacecraft right now suggests that there isn't a solid compact core, that material in the core, that rock and metal, has somehow been mixed into the hydrogen. And people have gone, huh, that's weird. Did something disrupt the core? Like, was there a big impact or something like that? But more recent work is starting to indicate that might not be the case. And this is coming from the other way of trying to figure out what's going on deep inside the giant planets, which is actually seismology. Remember, seismic measurements are what allowed us to see all of the internal structure of Mars and Earth. Now, you can't put a seismometer on a giant planet. It doesn't have a surface. But that planet does oscillate. And since the planet's surface, the planet's atmosphere is oscillating back and forth, you could potentially measure things like red shifts and blue shifts. People have tried to do this and have barely measured it for Jupiter. Not enough to really constrain things, but in the future, it should be possible to do this. While this is still being worked on for Jupiter, it actually has been done for Saturn. Saturn has this collection of rings, which we'll talk about more in the next presentation. But for the practical purposes of this presentation, the rings are basically a bunch of particles in orbit around the planet, and they're really sensitive to the detailed structure of the planet's gravitational field. Turns out you can use these to see certain types of oscillations inside the planet, including ones that get very deep. Now, studies of these have revealed that Saturn's core is also not a discrete thing. The outer layers of the core are mixed into the hydrogen envelope again. And that mixing layer is actually pretty big. And so when we do, what these measurements have allowed people to do is make measurements of what the density of the planet is as a function of distance from the center to the surface, which are shown here as plots for people who like plots. This is an uncertainty. These are showing as images here with different colors showing different densities. The main thing to show is the density never jumps. If there was a discrete rock and metal rich layer, the density would be going up as you go in and then jump and then have a jump at some discrete location. This doesn't seem to be the case. So there doesn't seem to be a solid rock metal ball in the center of either of these planets. It just becomes progressively more rocky and metallic and iron rich, since hydrogen's already metallic, as you get towards the center. So even the center of the planet doesn't seem to have discrete layers. So again, if you could survive falling, there is literally no surface that we can discern. There would be a point where a human would become buoyant, but there is no surface. These are truly alien, fluid-rich worlds. And I think that's remarkable. Thank you very much for your time and attention.